So, as a reminder, last time we were dealing with dependent versus independent events. The dependent ones are the ones that affect each other. The independent ones are the ones that don't affect each other. You guys remember doing this from last time? And so we said if we have independent events, then the probability of A and B both happening is simply the probability of A multiplied times the probability of B. By the way, don't always assume that. There's all kinds of examples where people have assumed independence where it's really not there. So don't assume always independence, but there you go. And then we did independent multiplication with the roulette example. So probability to roll 2 greens in a row, you can say, well, the classical probability of rolling 1 green is 2 out of 38. So 2 greens in a row would be 2 out of 38 times another 2 out of 38, right? And we did that kind of thing. All right. And then at the end, this was the last one we did, find the probability that you get 3 reds in a row, or that you get a green, then a red, then a black. Okay. And let's do this last one just to remind ourselves what we did. 3 reds in a row. So probability of getting a red on the first, a red on the second, and a red on the third roll of roulette wheel. So the probability of getting those 3 red 3 times in a row, since red is 18 out of the 38 total numbers, 18 out of 38, 18 out of 38. I believe this is the last one you have, so in your notes. So 18 times 18 times 18. I forgot what that was. You can use exponents too. 5832 divided by 38 times 38 times 38, which is 54,872. Okay. So that's what we did last time, right? This independent events where these probabilities all came from just knowing how to deal with classical probabilities. Another situation in which independent events show up is when we pick individuals over and over and over again from a really large group, like the US population. So, for instance, in the United States, there's like 300 plus million people, maybe 350 million people, somewhere in there. And if you pick somebody out of that group, it's not going to change the probability of the next pick. So let me give you an example here. So according to a Pew Research poll, 4% of the population identifies as atheist in the United States. All right. This was a poll about religious affiliation, I believe. So if 4% identifies as atheist, if you pick one person, the probability that that person is atheist is 4%. If you pick a second person, regardless of what happens on the first person, it's still 4% because really that 4% didn't change on your second pick. Does that make sense? So if you're picking from really, really large groups and you have approximate percentages, you can assume independence. Now, I want to be very careful about this. If you're picking from small groups, it's different. Here I have 5 markers in my hand. 3 of them are green, and I have a red and a blue. If I said, what's the probability of picking green on the first pick? You'd say, well, there's 3 out of 5. Everybody agrees with that? If I put all these in a bag and you had to pick randomly. If on the first pick you pick a green, on the second pick, the probability is 2 out of 4. However, on the first pick, if you pick the red, for instance, on the second pick, it's 3 out of 4. Notice how that probability changed from the first to the second pick, depending on whether I picked a green one or a red one. Okay, follow that? So if you have low numbers of things, then the probabilities are going to change from the first to the second pick. But if you have really high numbers of things, like you're picking out of the US population, then that 4% number, it's going to change in such an insignificant amount that we can assume it's still 4% on the second pick, and on the third pick, and on the fourth pick. Does that make sense? So we can assume independent multiplication if you're picking out of really, really big groups and the percentage doesn't change from your first to second pick. So let's ask the following question. What's the probability that you pick 2 people and both identify as atheists? So you pick 2 people at random and both identify as atheists. Well, we're going to take the probability of the first person being atheist, which is 4%, and then we're going to multiply that times the probability of the second person being atheist, which is again 4%. I just typed that into my calculator and I get 0.0016. Does that work? .0016. And I believe I've talked about this a number of times, but make sure when you're writing down probabilities, you go out to 4 decimal places. That's what we're going to be doing for the most part. Okay. I want you to try these on your own. What's the probability that you pick 2 people at random? The first is not an atheist. And the second is an atheist. What's the probability of 5 people and all are atheists? Once you get those done, I want you to try the following same things. Pick two people and neither identify as being atheists. What's the probability you take 20 people and none identify as being atheists? All right. So, by the way, in this poll, I think I said this, but I didn't say this, but the thing said it. People who identify as being atheists is 4%. Therefore, those who do not identify as being atheists would be 96%, right? By everybody else, right? 4% versus 96%. So when we're asked what's the probability that the first person is not an atheist and the second person is, then it's 96% multiplied times 4%, or as decimals, 0.96 times 0.04. And then the answer would be 0.0384 as a decimal rounded to 4 places. Now, what's the probability that you pick atheist 5 and you get 5 people and you get atheist all 5 times? Well, that's a 4% probability times itself 5 times in a row. Instead of writing times 0.04 times 0.04 times 0.04, I'm simply going to raise that to the 5th power. Okay. Because that's what multiplying itself 5 times in a row means. Raise to the 5th power, that's what that means. So 0.04 to the 5th power is 1.024, and then it says E negative 7. If you remember what that means, that E negative 7 essentially means times 10 to the negative 7th power. That's the calculator's way of doing scientific notation. 1.024 times 10 to the negative 7th. I rounded this number to 2 places. And by the way, times 10 to the negative 7 means you get let's see. Yeah. It's that probability. Lots and lots of zeros and then a 1, 0, 2. Okay. Does that work? Makes sense. If you do have one that comes out in scientific notation, it'll describe how to write it in Moodle. Usually, if something comes out in the scientific notation in Moodle, it'll be formatted like this. Something times 10 to the some power. And you'll have to round this number to 2 spots, and then you just have to put the power in there. Okay. So that's usually how that goes. Most probabilities we round to 4 unless we have scientific notation. Then we stick to rounding in the front. All right. Not, then not again. Well, not is 96% times another 96%. So 0.96 times 0.96 gives me 0.9216. And then the last one, the probability that you pick 20 people and none are atheists, that's basically getting not 20 times in a row. So we're going to take that 0.96 times itself 20 times in a row. It's easier to use exponents. So I'm going to use 0.96 to the 20th power. And when you type that into your calculator, you end up with 0.4420, rounding to 4 decimal places. Is that all right? So that's the idea of independent multiplication. Okay. We saw doing this using classical probability on the roulette example, and now we see this using picking over and over and over. Using this would be a given empirical probability because it's using collected data, collected from the poll specifically. Remember that? Empirical data is using collected data, whereas classical assumes equal likelihood. So this is empirical collected data. Okay. Okay. So now let's move on to dependent events. Remember that dependent events are events where the outcome of one is affected by the outcome of the other. Now, because we have outcome of one being affected by the outcome of another, we're going to have some special notation for dependent events. And the notation is going to be probability of A vertical slash B. This is the probability that A happens, given that B has already happened. So it's the probability that A happens, given that B has already happened. And that's the probability that we're going to calculate in this class. It's sometimes called conditional probability as well. The probability of dependent events is often called conditional probability. And there's a specific rule, excuse me, for this conditional probability. It says that if I want to find the probability of A, given that B has already happened, that's going to be given by the probability of the intersection of A and B divided by the probability of B. This is the probability rule. Now, I don't get it. Oops, hit the wrong thing. Now, I want you to write this as well. Thought I had it on the next slide, I do not. This thing, this rule is written in probabilities right now. But you can also write it in just sheer size of the sets. So you can also say it's the size of the intersection divided by the size of B. And that one's going to be a little more straightforward when we get to what's called the contingency table, which is our next slide. So that rule that's generally written in terms of probabilities can also just be written in terms of the size of the set. So it's the intersection divided by the B. And here, take note that the B is the given part. B is the given part. Does that work? Let me do an example using what we call a contingency table. All right? A contingency table is a table where we break down a certain phenomenon in two different variables. And we look at the options for those two variables. So the two variables here are what color the cars is, color the car is, versus if the car was speeding or not. All right. Now, these data are from a total of 12,000 cars. And it shows if the car was speeding or not, and also if the car was red or blue. All other colors they've ignored for this table. All right. So you can see that out of the total of 12,000, the total number of red cars is this 7,500 number. Of those red cars, 6,800 were speeding, and only 700 were not speeding. There was a total of 4,500 blue cars. Of the blue cars, 4,300 were speeding and 200 were not speeding. And then if you look at the speeding, out of the speeding, there was a total of 10,100 speeding cars and a total of 900 non-speeding cars. Everybody get what those numbers are telling us? Now, we're not going to do contingency, or we're not going to do the conditional probabilities yet. Let's start out by saying, what is the probability that you pick a red car out of the entire group if you pick a car at random? So I pick a car at random. What's the probability of the car being red if I'm picking out of the entire group? If I'm picking out of the entire group, what should be my denominator? Well, my denominator should be 12,000 because I'm picking out of the entire group. You're picking out of the total number of 12,000 cars, right? Of those that are red, 7,500 are red. You understand that? So if you're picking out of the entire group, your denominator is going to be the 12,000. And your numerator is going to be whatever trait that you're looking for. In this case, it was red car. So 7,500 out of the 12,000. And then again, if this were a Moodle, you might have to divide and get a decimal and write that as 0.625. Right? The decimal isn't the important thing. You can do that, on the back end. But there you go. Now let's take a look at how dependent probabilities would work. It says, what is the probability of being red given that the car was speeding? If I was given that the car is speeding, essentially what I'm doing is I'm just looking at this line here, right? Therefore, I'm no longer picking out of the entire group of 12,000, but I'm only focusing on the speeding group of 10,100. Everybody get that? So if I'm given that the car was speeding, now my denominator is how many speeding cars there were, 10,100. And of those 10,100, how many of them were red out of the speeding group? Well, pretty clear, hopefully. Out of the speeding group, 6,800 were red. Again, since I'm picking out of the speeding group, I'm not using anything other than the speeding group and the red cars within the speeding group. Does that make sense? So I'm putting in 6,800. Now I put that out because that's exactly what this rule is saying. All right? It's saying that if you're given B, now you're picking out of the group. So in my case, we picked out of those cars who were speeding, the total number who were speeding. And in the numerator, it was those who were speeding and red, because we had to pick the red cars that were in the speeding group. All right? So the red cars who were also speeding, that was the 6,800 out of the speeding group. Does that make sense? Where this rule's coming from? Now, since you're picking out of the given group, the size of the given group goes into the denominator. And since you are looking for this property, but within this group, it's those with this property who are also within the group. So it's the red cars who are also speeding in our case. Does that work? All right. So here's what I'd like you to do. The two questions, well, there's three questions in front of you. Two that require you to answer probabilities. So the first says, what's the probability of speeding given that you choose one of the red cars? And then the second says, what's the probability of speeding given that you choose one of the blue cars? And if you look at those data, answer the third question that says, well, would you expect more red cars proportionally or blue cars proportionally to be pulled over more often? So probability of speeding, given that you have a red car, probability of speeding, given that you've picked a blue car. Probability of speeding given a red car, probability of speeding given a blue car. All right. So if you look at that contingency table, when it asks you the probability of speeding, given that you picked a red car, the denominator is going to be all of the red cars, which on that contingency table, there were 7,500 red cars. In the numerator, it was going to be those red cars who were speeding. So red and speeding. And there were 6,800 red cars who were speeding. Now, just so I don't have to write this down again, as a decimal, that's 0.9067. Okay, rounded to 4 spots. Now, in terms of the blue cars, if we're looking for the probability of speeding, given that we've picked a blue car, total number of blue cars goes into the bottom. That's 4,500. And those blue cars who were also speeding goes into the top. That's 4,300. When I do that, I end up with 0.9556. Now, given this result, you might look at this and say, well, there is a slight difference in the probability of speeding, given the fact that it's a red car versus a blue car. And we see that these data show that the blue cars were speeding at a higher rate. Or I should say, to avoid confusion, blue cars were speeding more often. And that's what these data show. So you would expect that blue cars are pulled over at a higher rate. If if you're speeding more often, you'd expect that those people who speed more often are probably pulled over more often in comparison, percentage-wise, than the other. So if somebody said, well, the police are targeting blue cars, it might be the case, but it also might just be that blue cars are speeding more often, right? These are the kinds of things that you have to, these are the kinds of probabilities that you have to think through when you see, certain disparities. In this case, pulling over a red or blue car. Any questions about this? All right. Now, we've dealt with the contingency table version of dependent probabilities. Now let's take a look at using the probabilities directly to calculate dependent probabilities. Or, like I said, these are often called conditional probabilities. It's find the probability of A based on the condition that B has happened. Does that make sense? So it says there's a group of doctors out there, and the probability of when you pick one doctor out of the group, that doctor is male, is 0.42. So by default, the probability that the doctor is female is 0.58. The probability of having blue eyes is 0.32. The probability of picking a male with blue eyes, so that's with both traits of being male and with blue eyes, is 0.10. And the probability of picking a female with blue eyes is 0.22. Notice that the male with blue eyes and the female with blue eyes, those two probabilities add up to the total of blue eyes in the group. So 0.10 plus 0.22 is 0.32. Right? These two have to add up to those because those are the only options. So we're going to answer the following questions. We're going to say, what's the probability of being male given that you picked somebody with blue eyes? So probability of male given that you picked somebody with blue eyes. And then what's the probability of having blue eyes given that you've picked the male? You've picked a male, excuse me. So what's probably male given blue eyes? What's probably having blue eyes given that you're male? All right. could try to create a big old table, but it's easier just to use this rule directly, right? So if I'm looking for probability of male given blue eyes, I'm going to create a fraction. In the bottom of that fraction is going to be the given of having blue eyes. In the top of that fraction, it's going to be those with both traits. And in the last example, we use raw numbers, but here we're given probabilities. So we're just use probabilities here. Male with blue eyes, that's the 0.10. Right, the both traits, 0.10. And blue eyes, that's the 0.32. So it's 0.10 divided by 0.32. And whatever that happens to be, you would type that into, in this case, it's 0.3125. That makes sense? And then the second problem says, what's the probability of having blue eyes given that we've picked the male? In this case, if we are given that we've picked one of the males, the total number of males goes into the denominator. And those males with blue eyes, with both traits, go into the numerator. Notice you get the same numerator in both cases of 0.10. But now, since you're picking the male, you're picking from the male group, the denominator is now 0.42. I ended up getting about 0.2381 when I rounded to 4 decimal places. That makes sense? So you can use either the raw numbers or the probabilities in a situation of trying to find conditional probabilities. Raw numbers would come from things like contingency tables. Probabilities would maybe just be given to you. Is that all right? I want you to do the same thing with those same numbers, except this time, use female instead of male. What's the probability of being female given that you have blue eyes? And what's the probability of having blue eyes given that you are female? In this group, obviously. All right. Let me go through this problem. So, probability of being female given that you have blue eyes. The denominator is now the blue-eyed group. The numerator is the females with blue eyes. If I had raw numbers, I'd use raw numbers. But since I have probabilities, the denominator is going to be 0.32. And the numerator is going to be 0.22. Females with blue eyes is 22% of the group. Blue eyes is 32% of the total group. So I just take 0.22 divided by 0.32. And you end up with 0.6875. That's exactly it, but if you had to round 4 decimal places, you do that. The blue eyes given female, in the denominator, since you're given female, you're picking out of the female group. Those females with blue eyes is going to be my numerator of the fraction. Females with blue eyes, once again, is 0.22. Out of the total females, which is 0.58. So 0.58 goes into the denominator, 0.22 goes into the numerator. And I got 0.3793. Again, that's rounded to 4 decimal places. Any questions about dependent probabilities? How to find these dependent probabilities? And again, you'll see that, the probability of being male, given that of the blue-eyed group, is different than the probability of being female. But having blue eyes, given that you're male, is different than having blue eyes, given that you're female in this group. Okay. So those are little interesting tidbits. Again, that's of this group. Those are made up numbers. So don't dig too deeply into that. That's just numbers that we made up. Does that work? All right. Now that we've done a lot of calculations of probabilities, we're going to use those in insurance examples. So we calculated a lot of different probabilities. And now we're going to see how those probabilities can be applied in insurance examples. Okay. A lot of people think insurance is really difficult to understand. All right. But really what's happening is just insurance is balancing the probabilities of something happening with the payments that the insurance company is going to have to pay out, given that that event happens. All right. So it's just a balancing process. So we're going to look at this in one of the easier scenarios, and that's in the scenario of life insurance. So hopefully everybody understands what life insurance is. It's an insurance that I can buy, I can purchase, And how it works is if I die, then my family gets the payout. So let's say I buy $200,000 worth of life insurance. What that would mean is that in the event that I die, my family would get $200,000. Okay. And what happens if I live? Well, they don't get anything. And for this insurance, I have to pay, a certain amount every month. How much somebody is charged for life insurance is just a balance of the probability, the chance that they die, and how much the company has to pay out. So if they have to pay out $300,000 to my family if I die, that's going to cost less than if they have to pay $1 million to my family if I die. Does that make sense? All right. Now, in actuality, insurance companies have really elaborate statistics and models to figure out the probability of somebody dying within the year. Okay. We don't have access to those because the insurance company models of dying are kind of kept secret from the public, okay? They don't want their competitors to have their models either because they're proprietary. So instead of using the chance of dying based on some insurance companies' models, we're going to use the actuarial life table from the Social Security Administration. And the only thing you have to do is, well, you won't have to do this on the test or anything. But what I'm going to do today is I'm just going to go actuarial life table. And the first one that almost always pops up is the Social Security Administration's actuarial life table. Okay. Now, the Social Security Administration breaks down their table into a number of different categories. It's kind of like a contingency table in some ways. They group by male and female, and then they group by age. And based off of data that the Social Security Administration has collected, they say a 4-year-old male's probability of dying would be 0.000154. And again, what they've done is over the last however many years they've been collecting data, they've seen how many 4-year-olds have died in the United States and how many 4-year-olds have lived. Okay. And so they just make a fraction, how many 4-year-olds died, divided by a total number of 4-year-olds, that year. And they come up with that number, 0.000154. Everybody get that? Figure that out. By the way, an interesting thing is look at the distinction between male and female's death probability. At 4 years old, males are more likely to be dying than females by a little bit. In fact, at every age, males have a higher probability of death, even at 0 years old when they're first born. And when they're 1 year old, 2 years old. It gets the closest at 10 years old but then it starts going back farther apart. Okay, so there you go. Death must be sexist against males, right? No, it's just how biology is. Okay. So, anyways, that's where we're going to get our probabilities of death from. Is that okay? Now we're going to do that in this class period, but in the future, on future problems on the homework, on future problems on the test, I'll just give you the death probability. Is that okay? Because there's a lot of actuarial life tables out there, and they get updated every so often. So Social Security Administration is probably not the greatest one to use. I'll talk about why that is later. So like I said, what they're going to do with this life insurance is they're going to balance the probability of you dying with how much money they're going to have to pay out. And the official statistical term for that is finding the expected value. The expected value is essentially an average or a mean of a probability experiment. The way to think about the expected value is if you did lots and lots and lots of experiments over and over and over again, what would be the average of all those experiments? Does that make sense? So if I insure lots and lots and lots of the exact same type of person, what would the average payout be? Or what would the average be? So the expected value is the average of the probability experiment. Okay. So let's do an example. This says a person buys $150,000 worth of life insurance. For $200 per year. The probability of that person dying is 0.0012. Find the expected payout of this situation. And then it also is going to ask us for the expected profit in this situation. How much is the insurance company making on average? All right. Does everybody get what's going on? Let me kind of draw. So this person is buying life insurance from the company. Now here's how this life insurance works. There's two options. If the person dies, that person is going to get $150,000, or the person's family, I should say, is going to get $150,000. However, most people are not going to die. Most people are going to live through the year. So the person's family, if they live, gets $0. So we have a die option and a live option. These two arrows going out give us two options. And when I say pay out, that's what I'm talking about. It's how much is the insurance company going to pay this person's family? As you can see, it's going to be either 150,000 or zero. Now the person is going to pay in what's called a premium of $200 for the year for this policy. Everybody okay with this scenario? So when we want to find the expected payout, all we have to do is say, well, we want to find the average payout. The probability that the person dies, it's in the problem set based on the empirical data, is going to be 0.0012. So I'm going to take this payout and I'm going to multiply it by the chance that the person dies. Now, technically, you should also multiply the payout of 0 times the chance that the person lives as well. But what's going to happen when you multiply 0 times anything? It's going to be 0. Does that make sense? So this is not going to be impacting my total expected payout. So the expected payout is simply going to be the $150,000 times the probability that the person dies. That becomes $180. All right. Does that make sense? Why we're doing it the way we're doing it? This happens. This payout happens. This probability of time. This payout happens. This probability of time. So I just take each payout times the probability of it happening, and then I add those up. And I get my total average payout. Now, what this is saying is that if lots and lots and lots of copies of this guy walked into the insurance company, most of the copies are going to live. Just a few copies would die. And the insurance company would have to pay out $150,000 some of the time, but 0 most of the time. And on average, for all kinds of copies of this guy, on average, they pay out $180 per copy of that person. Okay. Think of like some sort of concept like a multiverse, where in a billion different universes, this person walks in. Well, this percentage of the time that person's going to die, this percentage of the time, this probability of time, person's going to live. And so on average, $180 per copy of that person. Okay. Now, here's where this comes into play. If we're talking about the average profit, well, we're going to be given
we're going to be paying out $180 on average per person, but we get in 200. So if we are the insurance company, we're getting in 200, but we're paying out 180 on average per person. And so the expected profit is $20. Did you get that? All right. Well, we are out of time. I'm going to pick this back up on Thursday. All right. So on Thursday, we'll pick this back up, and we'll talk a little bit about the test as well on Thursday. Okay. All right. Other than that, I'll see you Thursday.